The optimum design requires iterative numerical work, hence, machine computation greatly simplifies the optimization task. In this book, we shall limit the problem to answering design questions for a single set of design conditions. Even for such a limited scope, we shall find that the numerical integration often require repetitive calculation well suited for machine solution. As mentioned in section 1.1, the first step in a logical design procedure is to obtain a suitable expression for the rate of chemical reaction process, and this requires experimental data. The data can be obtained in one of three ways. First, from a bench scale laboratory reactor designed to operate at nearly constant temperature. Operating condition and reactor type are chosen to facilitate separating the effect of mass and heat transfer. The physical process from the observed measurement so that the rate of chemical step can be accurately evaluated. This is the most successful of the three methods. The example in chapter 2, where all illustration of this procedure and isothermal well mixed batch reactor was used to obtain concentration versus time data. Isothermal flow reactors also may be used in obtaining data from which a rate equation can be obtained. Analysis of data from such laboratory flow reaction is discussed in chapter 4. Second point, from a small scale reactor pilot plane in which the composition, temperature and pressure may change. Here calculation similar to but the reverse of the design steps are required to evaluate the rate of the chemical reaction, accurate separation of mass and heat transfer effects from the intrinsic chemical step may be difficult because of change in temperature and composition. Third point, from a commercial scale reactor which happens to be already available, the problems in obtaining an expression for the chemical rate are similar to those in method 2, but are usually even more severe because there is less instrumentation and hence fewer data. As an illustration of the first two methods, consider the oxidation of sulfur dioxide. Suppose that an ArSO2 mixture flow over particles of solid catalyst in a tubular flow reactor. In the bench scale study, the reactants would be passed over a very small amount of catalyst, and the rate of production of sulfur trioxide would be determined by measuring the rates of flow and composition of the inlet and exit streams. This production rate divided by the mass of catalyst would represent the global rate of reaction. For example, in grams of sulfur trioxide per hour per gram of catalyst, it would approach a local rate rather than an average value because the amount of catalyst is small enough that the temperature, pressure, and composition change is passing over the catalyst bed are similarly small. In the second approach, the amount of catalyst in the pilot plant reactor is sufficient to cause considerable conversion, and the temperature and composition may change appreciably as the mixture flows through the reactor. Since the rate of reaction is a function of these variables, it varies from location to location, and the major production of sulfur trioxide represents an integrated average of all the local rates. To reduce the major results, called integral conversion or integral reactor data to the rate of the chemical steps, requires a procedure that is the reverse of the design calculation. The integral method mentioned in chapter 2 could be used. First, a promising rate equation is assumed. Then the local rates are integrated through the catalyst bed, with the effect of diffusion and heat transfer taken into account. Finally, the predicted conversions are compared with the experimental results. Repetition of this procedure will result in an equation for the rate of the chemical steps. Because of the inaccuracy in accounting correctly for the composition and temperature change, it is difficult to arrive at a rate equation that is wholly satisfactory. Data obtained in both bench and pilot plant equipment are valuable, and it is common practice to carry out investigation with both before building the commercial scale reactor. The first yields a better rate equation and more knowledge about the kinetics of the reaction. That is, it tells the engineer more accurately just what variables affect the rate of the chemical step and how they influence the course of the reaction. This information is particularly valuable in case it is necessary to predict how the commercial scale plant will be affected by a change of operating condition not specifically considered in the pilot plant work. A bench scale study alone leaves the engineer largely dependent on correlation and estimates for the mass and energy transport terms in the conservation equation needed to calculate reactor performance. Experimental data obtained in a pilot plant can provide a check on the suitability of the design procedure. As an illustration, consider the extreme case where the kinetics studies are carried out in a batch tank reactor with diffusion resistance, and the commercial unit is to be a tubular flow reactor. The diffusion rate will not be the same under batch and flow condition. Hence, the observed global rate in the batch reactor will not be directly applicable for design calculation in the commercial unit. Will the importance of such effect can be estimated for different types of reactor as explained in chapter 10. The uncertainties in the estimates are sometimes so large that experimental verification from pilot plant data is desirable. There are similar problems with temperature difference arising from heat transfer considerations. Even where the kinetics studies are carried out in a flow system similar to that to be employed in the large plant, pilot plant investigation provide invaluable information on such important factors as temperature distribution in the reactor, materials and methods of constructions, and the effect of specialized design features. The procedures for extracting a rate equation from experimental data and the procedure for designing a commercial scale reactor using an available rate equation are similar. In principle, one is the reverse to the other. However, if a bench scale unit is used to obtain the rate equation, there is enough flexibility in design to eliminate many of the transport effects. From this standpoint, the interpretation of bench scale data is easier than the reactor design problem.